equation.
Okay, wow. Okay, well, good afternoon. Okay, welcome to the exam review. Okay, let's buckle down. We've got a lot of ground to cover. Not as much as I thought we'd have last week, because we were going to do Ampere's Law, and I assume you all know that Ampere's Law isn't going to be on the exam. The slides that I have at the end. I've got Ampere's Law, and I've got that included on the PDF file that you can download. Dr. Young sent you a link to that. If you've already done that, I actually have made quite a few adjustments with the idea that if Ampere's Law isn't on the exam, something else has to be. So I'm going to try to help strategize with you and try to figure out a little bit of what he might ask. And I've got some extra things that hopefully will hit certain areas a little harder. So let's see if that happens. Okay, let's just first start off with the idea of electric current. This is new. In the last section, we were dealing with electrostatics. And in electrostatics, the electric field, what about inside a metal for the electric field? Zero. And the argument was, if it wasn't zero, what would happen? Charges would be moving. And so that's what we have here with, let's say this is some kind of a wire. We need to put an electric field on it. We can do that, maybe connect it to a battery, and then we can set up an electric field here. And then charge will start to move. It's kind of rather complex motion. Electrons turns out it's what we're moving. When they're first dealing with this as far as current, they didn't know whether it was plus charges moving or negative charges are moving, or maybe even both. It turns out actually both do occur. In wires, it's going to turn out it's the electrons, and we're going to get to the point in here where we can figure out how we know that. But so an electron banging around inside with an electric field, it gets accelerated, and then it's going to collide with atoms. I don't have all the atoms here, and they start to kind of take a random walk where they will overall start to drift in the direction, being negative charges, go up the electric field. Keep in mind the electric field is like from a positive charge, they're attracted to that positive, and they're going to move that direction. We can take this idea, and I call it an idealized current. Think of this more like a tube of toothpaste. You kind of squeeze it, and it just kind of comes out. You've got to consider that all your charge carriers, and I'm using the positive current convention, are all drifting along with the drift velocity. And if we have a section of wire L, it's got a certain number of them. Now, the idea of the current is going to be how much charge goes by in a particular time by some cross-section. So these things, kind of like a marching band, are going through here, and we need to keep track of how many coulombs per second are going through. That will tell us the current. And 1 ampere is going to be 1 coulomb of charge per second that goes past a cross-section of the wire. If we want to get into how much charge goes across here, there's this idea of the number density. We've got all these charges in there. How many do we have? Well, this small n represents the number density, the number of charge carriers in a cubic meter of material. Now that's cubic meter is pretty big, and but we want to keep everything SI here. I want to specify that out from the outset. The units can get really messy in electromagnetism, but you'll be okay with units as long as you go SI all the way. You know, meters, kilograms, seconds. You have joules. You've got watts. We're going to have Tesla. We're going to have currents and amperes. Everything's going to be just fine as long as you stay with SI units. Okay, my little speech on that before I forget. If we take this number density, that's how many per cubic meter times the volume of this wire. Its cross-sectional area times its length would be its volume, times that number density would be some big, huge number of charge carriers that are moving. We have the charge of a single carrier. Usually this is E for an electron, but just in general, it's just some Q. and it goes by and again in some time t. Now, as long as this is in motion, and I'm drawing this kind of idealized current where the very last charges need to go through. First, these guys go through, and then these guys are going to come later. And if we take in some time t, we're going to take a number of these to go through. This distance, L, will be L over the time that it takes for the very last ones to go through. That should be the speed that they're traveling, or this drift velocity. So hopefully this can make sense for you. So it's going to be, again, small n, the number density times the charge carriers times the cross-sectional area of the wire times the drift velocity. Now, something that's really useful is the idea of current density. Now, this isn't density in the sense of pure cubic meter, but in terms of a square meter. We look at the current density. It's an area density across the cross-section of this wire. And it's just whatever current is flowing through it across that area. And that would be, if I take this current I and take this and just divide out A, then we're just left for the current density is just the number density times the charge times that drift velocity. Current density is something we'd use a great deal with Ampere's law. We will have some use for this yet, but let's come across that when we get there. This is the current density. So this is kind of the basics of an electrical current. Okay, now let me go to the next slide. Okay, the classic one is Ohm's Law. The idea that for most materials, I'm not even sure I should say most materials, many metals obey what we call Ohm's Law. That is, when we place an electric field on them, we're going to generate a kind of a current density coming across it. It depends on this idea of the conductivity of the metal. And there is something, you have conductivity, we also have resistivity. They're just inverses of one another. And so usually we'll deal with the resistivity for the stuff we're dealing with. So if I take it to the other side as a reciprocal, and then that's going to be the resistivity, is saying the same thing as that. Now, this idea that obeying Ohm's law, this is a particular property of the material. The idea that if I double the electric field, I should double the current density, triple it, or triple the current density. They go up together. Now, not all materials is this true where it's a constant. One of these is going to be, it could be temperature dependent. We'll come back to that in a minute, but let's play with this idea of this simplified Ohm's law. This is sort of in, let's play with this. Current density is going to be the current over the area, cross-sectional area of the wire, times the resistivity should be equal to the electric field. Then if we take both sides and we multiply by the length of the wire that we have, times L, we have the electric field times that L. Since the electric field should be uniform inside, times and relative constant inside, that constant times the L should tell us what the difference in potential across the two ends of the conductor are. That's that voltage, or delta V. The idea that if I just rearrange some terms here, I get I by itself, and I group these other terms together, rho L over A, and we can give it a name. We're going to call that the resistance. It's tied to the resistivity of the material. The resistance goes up with length. The longer the wire, double the length, you'll double the resistance. It's inversely proportional to area. So the bigger the area, it's like a big pipe. You let the resistance would decrease, current would flow more easily. So this leads us to what we usually refer to as Ohm's law, kind of on the macroscopic size. IR is equal to delta V. And we really strictly say it obeys Ohm's law for some material as long as the resistance stays the same or constant. So if I double the voltage, I'll double the current, and so on. The thing is, most materials are also temperature dependent. So you might have something, this expresses really kind of a first order extra term is what it is. All of this stuff is not trivial at all. We really need some quantum mechanics and some solid state physics to really get at what's going on. But for our purposes, it's pretty good, and it has, over a wide range, it's pretty accurate. The resistivity is going to be proportional to whatever we start with. This is typically at some temperature, like 20 degrees Celsius. And then there's going to be a property of the material, some alpha temperature coefficient of the particular material. Oh, and he'd give you those values in the problem. So he maybe tell you the resistivity of the stuff, maybe its temperature coefficient. I'll do a problem here in a second, and we have that. Now, if this term is true for resistivity, we can go to this step by just going back here. The resistance is just L over A times that resistivity, and I can turn that into a resistance. So you can look at it from either this point of view or this point of view. Now, some of you, in fact, you were given a homework problem where it's actually beyond the scope of this course right now, in that most of you have not had Physics 123. In that problem, if you recall, the idea that the wire was going to, its length was going to get bigger with temperature change. Also, the area is going to get bigger, and this is really taking place in reality. So that you had something that was very similar to this in mathematical form, but you had to deal with the fact that the length had its contraction or expansion due to temperature. There is a relationship very similar to this in thermodynamics. Dr. Young indicated he left the problem on there, even though that most of you probably can't handle it. You can. Anything you're going to get on this exam, he said, I wouldn't go that way, because most of them, half of the class hasn't had thermodynamics. So here we're just going to keep this thing fixed. So if you want to go from resistivity right to resistance, you can do that with the assurance that, okay, we're not worried about the expanding length of this thing or the increasing area with temperature. Okay, wow. Okay, I hope that didn't sound too scary. I was trying to be reassuring. Here is a problem from the practice problem. The idea of 5 grams of copper formed into a wire of a diameter 1.5 millimeters. Resistance, the wire is measured to be this. Okay, what is the temperature of the copper wire? So he gives you the resistivity of that. He also gives you the temperature coefficient, which would be the alpha. And he also gives you the density of copper. So we've got to play with all of this stuff. And the first thing I did is actually focus on this last thing, the density of copper. And again, we want to do everything, just convert everything to SI units. So there's grams per centimeter cubed. You better do that. And so I've got it, density expressed in kilograms per cubic meter. Okay, a little conversion there. And then I go back to the basic idea of density, that it's mass over volume. The mass of this is just 5 grams of this copper, and over the volume, pi r squared, the cross-sectional area, times the length would be the volume. From this, we can calculate, the only thing I don't know is the length of the wire, but from that, I can get the length of the wire, okay? Now, from that, I can go on to start to answer the question. If I want to get this resistance, this is going to be the resistance after it's warmed, not at 20 degrees, is going to be this alpha delta T. So again, I can put in he gives you the resistivity, not the resistance. So he gives you the resistivity, so we're going to express that in terms of RL over A. He gives you that. We have the cross-sectional area, or we can easily get that, pi r squared, and he gives you the diameter of it. We have the length of it. We have the alpha. The temperature that we want to get is, of this resistance, is referenced to 20 degrees Celsius. That's near room temperature, so it's just a real practical way of defining these things, and R0 would be the resistance at room temperature. So what he has here is what is the temperature of the copper wire, okay, and it was measured, that is measured to be when it's hot, to be this. And then it's a matter of sticking in all the numbers. I've got everything except T. Little algebra, which you know how to do. I come up with a temperature of 0.914 Celsius. Okay. Okay, so just kind of a little bit of bookkeeping and kind of testing to see if you know those terms, and hopefully you would be able to put this together pretty easily. Okay, let's start off with some basic simple circuits. Way we're drawing this, hopefully you're getting used to these little square bent wires. This is a battery. We have the script E, which stands for an electromotive force, which is really a misnomer. Voltage is more of a energy kind of an argument. Voltage is the energy, potential energy per coulomb. So this really represents the potential energy that this thing will change the circuit with. If we connect it to a resistor with wires, these things represent resistanceless wires. They conduct freely, sort of like in 121 where we had frictionless surfaces. Consider that this is kind of frictionless and it allows the current to flow freely. And any resistance we have is all bundled up inside this thing called a resistor. Now, in order to get current to flow across this resistor or this wire, we need to have some potential difference across of it. Here it is connected directly to the battery, so its potential difference is going to be equal to that of the battery, both of these. And there will be some kind of current flow using Ohm's law, and we say that that current is going to be delta V over R, or E over R, if you want to use that. Okay, so this is just kind of a simple case to begin with. Associated with that is also kind of an electrical power. This form of the power is probably conceptually the clearest. The delta V represents potential energy per coulomb. The I represents the coulombs per second. So this will be in joules per second, and this is coulombs. Excuse me. This is joules per coulomb. This is coulombs per second. The coulombs will cancel, leaving you with joules per second. So that would be your indication. Hey, joules per second. This is the rate we're using energy. This is what we call the power. Now, this relationship, although this is conceptually the clearest, can be also combined with Ohm's law, where I can replace I with delta V over R times delta V. So we end up with a delta V squared over R. That also represents power. It really comes from this. And then one that gets used a great deal is this one, where I'll take I and I'll replace delta V with I times R. So we end up with an I squared R. And that's going to be the power. It's kind of your pick to do which one you want to use. Very often, again, though it's practically this, conceptually, I think this is the clearest. Okay. If we get into an idea of a simple series circuit, this is now the basic series circuit people get confused with. The idea of we're going to have some current flow, and that current flow is going to go through this resistor. The same current is going to go through this next resistor. They share the same current and will come through here. This is the idea of a series circuit, that the current is the same through all the branches of this series circuit, one to the next. Now the voltage, though, is the potential energy per coulomb. The idea here is we went up in potential a certain amount per coulomb, and then here we're going to go down. We refer to these as voltage drops. We're going to get current that's going to flow through here, but it's going to drop in potential energy. And this first one would be delta V1. And then there's going to be another drop called delta V2, and the sum of these two should equal the EMF of the battery. If you want to do a quick Kirchhoff's voltage loop around this thing, the same thing, plus E, and then I'm going to drop one here, V1. I'm going to drop another one, V2, back to 0. I just take these negatives over to this side. These will be negative. Anytime the current will flow through the resistor, the only way it's going to flow through there if this end is higher potential than this end. And same with this, higher potential than this. So we're going to sum those. We can do what's called an equivalent circuit by using Ohm's law on these two to get the current here. Current I, this top one is going to be I times R1. This is I times R2. They really share the same I, so I can factor that out. And so that I times the sum of those two resistors is what we'll call the equivalent resistance. Okay, kind of summing up, for a series circuit, you want to consider that the current is always going to be the same through them, and that the sum of the voltages or voltage drops across that resistance have to add up. So delta V1 plus delta V2 has to add up to that. Okay, I'm jamming through this stuff pretty fast. Hopefully this is clear for most of you. Another type of circuit, the simple circuit is, or relatively simple, is going to be a parallel circuit. Now a parallel circuit is probably the most confusing for people. The idea that I've got this resistor, it is connected to the battery, and also this one, R2, is also connected to the battery. Although it seems like it's a little more indirect, it still has a resistanceless wire back over here, so the potential difference from this side to this side is going to be the same as for this one. So things that are in parallel, we say they have the voltage is going to be the same across those two. But now in terms of the current, this current that's feeding this thing is going to be coming in. This current is going to get to this junction and it's going to want to split. Some of it's going this way, some of it's going that way. And call this one I1 and this one I2. So we have the total current coming in. Whatever's coming into this thing is going to come back out. This is going to form the basis of what we mean by Kirchhoff's junction rule. That we can take and add those two currents. They should equal what's ever coming into that circuit. We can replace the I with using Ohm's law. We can say I is equal to E over R equivalent is equal to your change in voltage for the first one over R1 is equal to, plus the change in voltage for the second one over R2. But all of these voltages, V1 is V2, those are all going to be equal to E. So we've got that. So we can go ahead and cross those out and cancel them. And then I have the idea of the equivalent resistance. 1 over R equivalent is 1 over R1 plus 1 over R2. And these are going to be in parallel. So the idea of a parallel circuit we want to have is that the voltage has to be the same across both of these. And the currents will have to add up. So there is a split in the current. They have separate currents, and they more or less operate independently. So hopefully you got that down here. Let's do a real quick thing. You might have a problem where you have to do some circuit reduction. So for instance, let's say you're given this. What kind of circuit is this? Is it a series circuit? Parallel circuit? Neither? Okay, this is more typical. Okay, okay, these two, are these two in parallel? They sort of look like, why are they in series?
Well, because the current has to go from one to the
Yeah, whatever current flows in here has to come back out here. So they sort of look like they're in parallel. They're not. So they really are in series. And so we can do a replacement of just adding these two up and come up with an equivalent. Now, are these two in series or? Parallel. Okay, they're going to be in parallel. I tried to keep the numbers real simple. So these two can be now, one thing with parallel circuits, well, I'll come to a better spot with this. Yeah, so these two are in parallel. So let's just continue simplifying this thing. So real quick, 1 over R equivalent ends up being 1. In fact, if these are the same, whatever you get in parallel, that's actually going to be less R equivalent. So anyway, you can do the math and come up with 1 ohm there. And then what about these two? These are series again. So we could just go ahead and add them. Do that. And we've got this kind of picture, and I probably should have chosen some values that weren't so obvious, but again, we've got 2 4-ohm resistors is the same as 1 2. So if we want, we can reduce the circuit to a single equivalent resistance, but if we want to get back, let's say he said, here's your circuit, I want the current in every resistor, the power consumed by every resistor. Could you give me the voltage across each resistor? You should be able to do that. And the way you'll do that with the circuit reduction method is you're going to really work backwards. You'll start here and just figure out, well, 10 volts and 2 ohms, this has got to be 5 amps through here. Then we go back to the next step. Okay, so that's back to here or here. We've got 5 amps coming out of the battery. That's going to stay the same. Here it's going to split. Now I could say that this is 10 volts and I can do 10 divided by 4 ohms is going to be 2.5 amps. Do the same thing here. I get also 2.5 amps, not surprisingly. And these two better add up to 5. 5 coming in, and I got 2.5 going out of through each branch. Then I'll step back one more step. I can come here. Well, this is pretty easy here because if I've got this 2.5 amps coming through here, it's got to be going. These are in series. Don't they have to have the same current? So that's 2.5. So we've got that. Then I've got, back up another step here. We're going back here. Now that I just had that. 2.5 amps is that. I need to jump over here. Okay, and then that 2.5 amps was really due to 2 resistors in parallel. So the fact that there is, I probably shouldn't have used these simple numbers. They have the current is going to split between them. They each have the same potential difference. I should have did something that we had to work a little harder here. I was trying to zip through this pretty fast. But these, where am I? Yeah, got these. So these 2 that were in series, this is the first one we dealt with, have this 1.25. So I've got the current in each of these. I have the value for the resistance. You can use Ohm's Law to get the voltage across each of these. I'm not going to bother to do that here, but you should be able to get that. You can use the power equation. I squared R would be a handy one. You've got the currents. You could get the power for each of those resistors. If you want to get the power out of this thing, all of this power that's being going out through, it's really, these resistors get hot. The energy or the power from that is causing them to warm up, give off their energy. It's coming from the battery. And if we look at 10 volts, think of power is voltage times current. That's 10 volts times 5 amps. That's 50 watts of power we're sending out through this thing. And if you go back and get the power from each one of these things and add them up, they'll exactly equal 50 watts. So these are kind of fun.
What are the chances that Professor Young is as nice on the exam?
Okay. Okay, this is simple circuit. So why did I do this? He will do it, and we'll come to some examples where he probably will, it would be where he maybe put some of it in. So we need to do Kirchhoff's relationships, but we could greatly simplify it with some circuit reduction. So that can take what would be maybe 10 equations and 10 unknowns, and we can start to pare it down to like 3 equations and 3 unknowns. So I'll use this actually in a couple of the problems where we use it for part of it. And so that's Otherwise, yeah, why do this, huh? Now, something that's more universal is doing this with Kirchhoff's laws, and we've got kind of two of them. One of them deals with the current, and this is kind of just formalizing what we kind of looked at with these other things. The idea that you have a flow current or current coming in, it's going to split and go out. That any junction, the sum of the currents must equal 0. Now, by the sum of the currents, we'll take something like maybe when the current's coming in, you might want to call that positive. Maybe negative when it flows out. So that overall it would add up to 0, your pluses and your minuses. You could call going out positive and coming in negative, kind of like Gauss's law. That's a good kind of an analogy for this. Okay, so I'll come to some examples with this. And then we also have this loop rule, which applies to the potential differences across the element as we go around the circuit. So if we have here's just a simple one that we could do with the other method, but let's just look at it from the point of view of energy. The idea that the EMF of the battery raises the potential, and think of this as kind of a potential energy thing. In fact, you can do some examples like this. Consider that the floor or the ground is 0 potential energy. This is what we did with gravitational potential energy back in 121. We'd say, okay, this is the ground or the floor. That's going to be 0. And then I come up to the tabletop. I get up to the tabletop. I've raised its potential energy, MGH. So consider that it's somewhat analogous to this here, that the EMF of this battery will raise the potential energy up. And then it goes from a higher potential, like from the tabletop, and it's going to, let's say, a marble rolling down a hill would go down and give off some energy. The idea that that potential difference is what's going to drive the current through this thing. Get down to point D. D is just a wire across here. We consider that doesn't change the potential energy. We get another ramp down with this other resistor, and we return to the ground. Or we could roll along the table. We get up to here, and then we're going to drop through this resistor, and that could be like rolling down the hill here. We get back to the ground or the lowest level, and we can do a complete loop. The idea that the voltages are potential energy per coulomb, so we can deal with this rise and the fall, regardless of whether I take this path or this path. As long as I come back to the same place, the overall change should be 0. So some simple ideas and very powerful. Then you're going to get something. This is going to be more typical of what you're going to get on the exam. Or at least you definitely will see one that's like this one. And here we've got 3 batteries. Is it a series or a parallel circuit? Okay, this is definitely none of the above. Okay, so what we want to do first with this thing is, and when you get any kind of problem like this, assign currents through each branch. Now, this I1, I'm not sure which way the current's going to flow. Generally, this long side of the battery is the plus side, and we get current coming out of it. So I say, oh, that looks good. I'll just call that one I1. This I1 covers the whole thing. These two elements, the battery and the resistor, are connected in series. So what's flowing into, or I should say what's flowing out of the battery here, I1 is going through the resistor. It's coming back. It's going to split. Ultimately, it's got to come back, and I1 has to come back into the battery. Whatever leaves the battery on this side has to come back into it on this side. Okay. I put in then also I3. I look over here and I say, wow, that's a pretty big battery. This was 10 volts, this is 30 volts. This is plus. Boy, it's got to power things, and it's going to send current in this direction. I'll call it I3. Then I look at this, and we got 2 of them coming into this junction. Can I have another one? This is the plus side of this one, and it should drive current that way. But I just assigned it this way. Okay? Now, a general rule here, you've got a couple junctions here and here. We're going to get these currents that are going to come in, they're going to split. They're going to rejoin over on this side. There's going to be some current relationships. Now, there's something I want to say here. Again, when I start this problem, you don't have to second guess where the currents are going. What you're doing is forming a sign convention. Like when I put this one, it doesn't matter. In fact, I did these purposefully wrong because the current I know is going to go the other direction, but the math is going to tell me, and so I don't need to guess. Sometimes you look at some circuits and you really can't tell which way the current's going to flow. So just assign this direction. That assigns a sign to this. So I just put I1, I2, I3 in this and in this direction. And then I proceed with the problem. So I want to first start off with the idea of the junction rule. I'm going to call anything that's coming in as positive. And so I pretend like I know everything I need to know. I have I1 coming in. I have I3 coming in. Both of these are positive. And I2 would be flowing out. And so they all should add up to 0. Or we could take I2. I2 is going to equal I1 plus I3. You just have to add up at that junction. If you want to do it around this one, you can get the same results. You're going to find this is going to be negative, that's positive, and negative. You get the same results. Okay, now there's also the junction rule.
John?
Yeah.
Could you explain why the battery doesn't affect that, the current?
The battery generally wants to drive current. Let me get this out of here. Wants to drive current from the plus side around to the minus side, okay? And it is possible, in fact, we're going to find out that this is negative. There's actually current flowing into the battery. What that is doing is that it's charging up the battery. So rather than the current and the energy coming out, we're going to be putting energy or current into this thing. And that's what you would be doing if you're charging a battery, okay? Yeah.
What kind of tripped me up is I saw like the middle says 2 currents coming in and current coming out.
Yes. Oh, yeah, okay, good point. I2, these two are connected in series. So even though it's a battery and not a resistor, whatever current it would be coming into this one, and if it's coming in, it would be charging this battery up. Whatever comes in has to come out and then go through this resistor. So I can say this is I2. I could label it here. I could label it up there. Anywhere on that series branch, I could label it. Same way with this one. I could have labeled it I1 coming in here or up there. I know that for this whole branch, it has to be doing that. And this whole branch is got to be I3. And so I've got to have I3 coming in, I3 going out, I3 coming in, going out. Okay, then I can choose, basically there's a kind of a quick rule of thumb here is I've got a couple panes here. And I've got 2 junctions. Now, don't try to use both junctions because this bottom junction is just going to be the equivalent of this. And you're going to end up with redundant equations. So I've really just got one. So the basic rule is count the number of nodes that you have basically and divide by 2. It's a kind of a rule of thumb. You can write it in such a way that it looks a little deceiving, but that's true. Then for the voltage loop law, we can usually best to use the smallest possible loops here. Let me show you how we'll do that. Okay, I'm just going to set up an arbitrary loop. I'm going to start down here. I'm going to go up, around, down, and back. And so I'll do that. And I go up on the voltage side. Okay, this is a plus 10. You want to look at the voltage. I'm going from the negative to the positive, so that's a rise of 10 volts. Then I get to this resistor. If the current's going through it, the only way it's going to happen is if there's a drop in voltage across here. So there's a voltage drop. It's going to be the resistance R1, which is 1,000 times I1. So I have that drop. Then I come to another battery. Now this battery, this is the plus side, this is the minus side. I'm going to be going from the plus side to the minus side. This is a drop of 20 volts. Going the other direction would be a rise. This is a drop. Then I've got the current going through R2. So again, this is another drop, voltage drop across that resistor. That goes in as a negative. Okay, and that's got to be equal to 0. Then I can do another loop here. I'm choosing to do this one going around. And I'm going to come here. Here I'm going to be going up, kind of upstream. I kind of think of this idea of current through a resistor. Think of like a mountain stream. If the current is flowing and you're going with it, you have to be going down the mountain stream. You are going down in potential energy. If you try to go upstream, it requires a rise in potential energy. So this first one is actually not a minus, it's a rise. I'm swimming upstream to get to here, so that's a plus. Then I get to the battery. Here I am going from the negative to the positive. So this is a rise of 20 volts. I then go across this resistor. Now again, I'm swimming upstream. So this, rather than being minus, is going to be a plus. Then I get to this battery here. I'm going from the plus side to the minus side, so that's a drop. And so this is how I'll set these up. And hopefully you can see the subtlety with the signs. That's going to be crucial if you're going to get the right answer. Then it's a question. I've got really 3 unknowns. I want to get those current. What is the current in each resistor? As long as I know what what these currents are, I can answer that question. I need to simultaneously solve these. And here's my answer. Okay. Now what you should do is, hopefully you can handle simultaneous linear equations on your calculator. I think Dr. Young alluded to that. If you haven't learned that skill, it's very handy and will be very useful. What I've recommended to people, rather than come up and ask me, I hardly use any calculators anymore, is to go to YouTube and put in your calculator model number and simultaneous equations or reduced row echelon form, and you're going to get a 5-minute video that's going to tell you exactly what to do. And it's going to save you a lot of time, rather than trying to do this the long way. Yeah?
Why do we draw loops in the same direction? So one clockwise second.
Okay, I just happened to do it here. And I probably, you don't have to. You can go the other direction. Let's say this second loop, we're going to run it in reverse. You'll find that if we're going to go the other direction, this would be a rise of 30. That would be plus. This would be a minus. All that's going to change is the sign of these. And that's it.
What are potentials of me making a mistake on exam if I will just decided to do it opposite way?
It works, again, just fine. You can also choose to do this outer loop. Now, but be careful. Don't do 1 loop and 2 loops and then a 3rd loop, because that 3rd loop is a linear sum of the other 2, and you have redundant equations. So I do need at least one current and 2 voltage loops. So in terms of how many loops you need, basically kind of look at like this is a window pane. I've got kind of 2 panes, and so use two of those. I've got 2 nodes, and divide by 2, I should have 1 current equation.
Gotcha.
And if you are getting your calculator spitting it back that it's not working, that it's giving you some kind of an error message, you have redundant equations. Now look at the results here that I got. I guessed wrong. I won. I come up algebraically with a negative. What does that tell me about the direction of I1? It's going the other direction. Now, and then same thing with I2. That's coming back out the other way. I3 is in the direction I indicated, and so that's positive. He would be okay with this as far as labeling things. It would be better to start off labeling these currents and then come back and say, oh, but they're negative, rather than get out the old eraser and start to kind of start the problem all over again, but say, no, it should have gone that way, which you can do, but yeah.
Will it be better to draw it on a circuit or just make a note on the side, go to the left and go into the right, up and down?
I would literally draw it.
Gotcha.
Yeah, keep the diagram very graphic, and I would put an arrow in the direction and label it I1, I2, I3.
Gotcha.
Okay. Okay. Oh, yeah, and this I1 was negative, so it is going in. Really, this 30-volt battery is charging up this 10-volt battery. Oh, I guess along with this one, I2 was negative, and so this is flowing out of this battery. So both of these batteries, this 20 and 30 volts, are dumping current in, power in, and it's being consumed over here by charging up that battery. Okay. Okay, now, okay, let's include some things of capacitance. This slide was really from our last review, just to bring back some memories here of capacitors. The idea of the capacitor is charge over delta V. It's always a positive quantity. The charge Q is usually there's a plus Q on one plate, minus Q on the other plate. We just have the absolute value of those. And then the potential difference across the plates. We can get that potential difference by taking E times the distance between the plates. We use that distance D. I don't want to take the time to do this, but we can quickly derive the capacitance of a parallel plate capacitor if we had to do that. Primarily what we're going to be doing, you'll have just some generic capacitor, something like this, one of these. But it's good to have this idea of the parallel plate capacitor in mind as a kind of conceptual bridge to what you're looking for. Okay, let's get into the idea of a simple charging. In fact, the symbol for the capacitor looks like a parallel plate capacitor, so that's appropriate. We've got the battery. If we want to charge this thing up, I can throw the switch, and we're going to get current that starts to come out of the battery. It's going to come in, and it's going to start to charge this capacitor. I've got this plus. There should be equal number of minuses on this side. So whatever current's coming in this thing, it starts to pile up, driving off an identical amount of current out the other side. So we've got I up here is going to equal the I through here coming back. There is these negative charges here. There's an electric field in there that is pointing down. So that indicates that there's going to be a voltage drop here since the electric field's in that direction. E times D is the voltage that we're going to drop across the resistor. Now let's do a little Kirchhoff's loop around this thing. We go up in potential, or E, and then we come to the capacitor, and we're going to have a drop here because I'm going from the plus side to the minus side, a little like was kind of imaginary, like a battery kind of. It's going to be minus Q over C. This is going to be the voltage across, or voltage drop, I should say, across the capacitor. I also have that current going, same current going through the resistor, and that's going to be a voltage drop here. And then I return back to here. That's got to equal 0. So this is just a little simple Kirchhoff's loop there. Then also I need to realize that I've got what's coming to a differential equation. The I is really dq dt. And so I've got a differential equation. I need to solve this. I'll take all of this over to the other side, dq. And I want to separate variables here. So I want to get q's on one side, t's on the other side. So I've got the q here. I'm going to take the dt over here. I'm just going to leave that rc. I could have brought it to either side. And I'm going to take this down underneath. So I've got q's over here, t's over here. And then I can integrate. It's a good idea to use limits to help you with initial conditions. They get to be kind of tricky on some of these. I'm going to start when I first throw the switch, 0, and then sometime t after I threw the switch is going to go from a 0 charge on the capacitor up to some value q, which corresponds to this time what the charge on the capacitor is. Now, this is just kind of calculus now. We need to solve this. U substitution is handy. I'll let you kind of work through the details on your own. We're going to end up with a T over RC. We've got this, which looks like it's going to give us a natural log. And so we're setting ourselves up for that. So we've got minus T over RC is equal to the natural log of this. We can get rid of that natural log by taking both sides, or take e to this power, and e to the natural log is going to tell you what's inside and give you that. So that you should be familiar with. We can do a little more arranging. I'm going to put it in this form. This is going to be E times C, which is going to be the charge of the battery, or excuse me, the voltage of the battery times the capacitance. Should tell me the amount of charge that's on here. Now let's just look for a moment here at what's going on. When I first throw the switch here, this capacitor has no charge on it, and so there's really no term here, and we really just have E equals IR. It's acting like just a simple wire when I first throw the switch. After a while, it starts to build its voltage, and it's going to ultimately build it to match the EMF of this. As this builds in potential, it wants to act kind of like a battery, drive the current the other direction. It's going to slow it down. And so this is kind of a pushback. Then when it finally gets charged fully, its potential should match the EMF of the battery. The idea that there'll be no current, it's all charged up, it's not allowing any more to go through. The voltages are the same. This wants to drive it that way, the battery wants to drive it that way, and they kind of balance. In this case, then there is no current flowing. The capacitor is acting like an open circuit. I want to come back to this idea. And there'll be no current flowing through the resistor. And the voltage on the capacitor is going to be the same as the battery. So we've got that. The Q is going to be the product of those two. And this is going to be the expression of minus T over RC. We often replace RC with what's called tau, the time constant. Now, just dimensionally, let's look at this. The idea that E to some power. Can a power have a dimension? Can you take an E to the...
No.
Right, it has to be dimensionless. So just in an inspection of this, we don't have to look too deeply into trying to trace our units back through, but R times C will have the units of time, right? Time divided by time would be a dimensionless number, and that's what we need to have. And so T, this is time constant, is just the product of the resistance times the capacitance. Now, I'll come back to this in a minute here. Okay, so the idea of the charging of the capacitor, I'm just kind of reiterating what I just did over there. And we kind of want to look at this. There's a lot of math here, so it's easy to get kind of confused what's going on. The idea of the charging of the capacitor is going to go up. It's going to start at 0. It's going to approach asymptotically some value, EC. If I ask the question, how long does it take to fully charge? How long is that? Infinity. It's approaching this asymptotically. But it's going to be decreasing. Now, what can be handy is this time constant, tau, is nothing really physically significant from it. It's more just a convenient thing to calculate. Just pull out your calculator, R times C, and what it will do is will not tell you when it's fully charged, but it will tell you when it's reaching a certain amount. Now that certain amount is when T is equal to tau, then this equation would just reduce to the Q max of 1 minus e to the minus 1. Now, for that, if you stick that into your calculator, you're going to get 0.632. Okay, that's just coming out of the math here. So what it is it tells us not what the full amount of charge is, but it will, after that amount of time, it's got a charge of 63.2% of the maximum value, or it's 63% fully charged after this tau. Okay. Lots of stuff to keep track of. Okay, now we can also get the current as a function of time. That's going to be equal to dq dt, so we just take this expression and take the derivative of it with respect to time, then that 1 will go out, and then we just have this term. So hopefully you can see that, how that pans out. And that the I max is going to be E over R. Now, what happens is when we first throw that switch, that current is at its maximum value. As the capacitor charges, that current slows and gets to be less and less. It starts off with as though this capacitor acts like a wire, in that we just have the battery and the resistor. We would have a current. That would be I max for just a battery and a resistor. It is going to decrease from there. We can play the same game with the time constant. When t is equal to tau, I max is e to the minus 1. And that's going to be 0.368, or about 37% of the current. So it's going to decrease with time, asymptotically approaching the axis. Okay. Okay, lots of... Whew. Okay, now we have the discharging of the capacitor. We've got some capacitor, let's say it's fully charged. Depends what kind of charge we put on it in the first place. We're going to start off with some Q naught. And just looking at this kind of conceptually, it's going to start with some Q naught, and it's going to, when we throw the switch, it's going to start to discharge. And it's going to come down. As the Q of the capacitor discharges, so would its voltage, since they're just directly related. Q over C is the voltage of the capacitor. We can do the same thing. Okay, let me back up here a little bit. We want to do a little Kirchhoff's loop around this thing, and this is nice. There's no battery. There's just the two of these things together. But we need to be careful of something here. The voltage across the capacitor. Let's say I'm going to do a loop this way. I'm going to go in this direction. I'm going to go here. The voltage across the capacitor is going to be the Q over C, or it's going to be the positive. I'm going to have a positive Q on this top plate. Then, yeah.
That Q with the T cross Q. It looks like the consign. The Q with the cross. Above that to the left. Second? Left. Yeah. Back. That's a Q, right?
Oh, this was a Q naught. Okay. I'm missing. Are you talking about this?
No, the Q with the cross. That's just a charge, right?
What you're pointing at?
Yeah,
The red top left Q.
Yes, that was.
Okay, this means Q naught. Oh, the bar through there is trying to do that sometimes for Q. We'll put that through. I think I've got that kind of in my notes.
that's just charge, right?
Yeah, that's just charge. It's the charge on the capacitor. Okay, and now that's going to be important here. As this current flows, when I throw the switch, I'm pretty confident that the current's going to go this way. It's going to leave here and discharge this capacitor. And normally we'd say, oh, I is equal to dq dt. But we need to be careful here. If Q represents the charge on the capacitor, it should be, as this thing discharges, should be decreasing. So we're going to really screw up our equations if I don't say that I is equal to a minus dq dt. Okay, this is a subtle issue. And so when I put that in for I, this is a minus, and now a minus dq dt, this goes positive. I'm going to take it to the other side and get the minus sign back there, but it's still there, and I need this. If I don't have this, then we're going to have kind of a runaway thing where this thing, the current's flowing, supposedly discharging it, and the charge keeps building and building and building, and so it's like this isn't going to work. So we've got this side. I'm going to take, separate variables again. I'm going to get my Q's on this side, my T's on this side. So I take this Q, I have a DQ, excuse me, I'm going to do the Q's on this side, bringing Q down. I'm going to bring the DT up on this side, and I can integrate that, and with a natural log again, and we end up with, did I take that? Yeah, I carried that through. Oh, this, I don't know where that should just be out of there. shouldn't be there. I really want to pick up the story here. I'm going to take this and I'm going to, I'm confusing myself now. Oh, this is current. I'm sorry. Going back here, I had it right here. The charge on this capacitor is exponentially decaying. This is minus T over RC. So this is this. It's going to be decaying like this. Again, either with RC or tau. You can express it either way. And again, this idea of tau, after a time constant RC, this thing has discharged to 37% of its charge. Or if you're doing voltages, 37% of the voltages. Now the current over here is going to be equal to a minus dq dt. I can just basically take this expression, taking the derivative, we end up back here. I think this is pretty straightforward. And then the I is going to be V naught over R, and it's going to be this e to the minus, so this is going to be this here exponential decay is going to be here. And this relates to V naught over R should be the maximum current. That maximum current happened right at time t equal to 0. When we first opened the switch, we had the maximum amount of current. We had the voltage across here. It's acting like a battery to drive current. And we can get that maximum current from just the initial voltage on the capacitor divided by the resistance. And again, it's going to decay and play the same thing with the time constant. Okay, kind of messy. You probably should at least, if you don't follow entirely what's going on, you just memorize these equations. That's probably good for the exam. However, yeah.
So I'm not sure if I'm wrong, but I have for discharging a capacitor, I applied max is negative, not positive.
Oh, Imax over.
Discharging should be negative. Well,
okay, now I've got that here. Okay, yeah, I took that into account from the beginning. I'm confident that if this is the plus charge and the minus, current will go this direction. Yeah. And also the Q on this, I don't want to say, oh, it's dq dt, because that represents the charge on the capacitor. So as this drops, the current would be the opposite sign. So this is plus, that is plus, but this will be minus. And so I picked that up here with that same sign convention. This is probably the trickiest part to the discharging in the capacitor, seeing this relationship or missing it, and then you mess up your math.
but that's just showing that like the direction of current changes.
Oh, right. Certainly. Now we could.
To charge it, it's going in one way, and then just it goes different.
Okay, yeah, okay. In fact, let's get to a more practical example as far as what he might do on the exam. He'll give you probably a problem like this, okay? Study the circuit above. If the capacitor is initially on-charged, what is the current through each resistor when the switch is first closed? You want to look for some key words like first closed. That's t equal to 0. Then he says, what is the current through each resistor after a long time? This is also another key phrase here, long time, which for us means virtually infinite. What is the current in the capacitor as a function of time after the switch is opened? Let's play with these three things. The first thing, when the switch is first closed, the charge, there can be a current going freely through and into the capacitor. In fact, when it's first closed, since there's no charge to begin with, there's nothing in there to push or pull either direction. The current can, in a sense, be charging up the capacitor. It comes in, it charges it, it goes out, and then goes through the resistor. C will act like a wire. So if we do that and put this in, now here's a classic case where we can use this as reductive circuits. I don't need to jump in and do a Kirchhoff's loop. I'll just say, hey, I'll just reduce this. If I replace the capacitor with a wire, then simplify it with a wire, then these two are in parallel. I can reduce that with an equivalent resistance. From that equivalent resistance, here's that, I can determine what the current is, and that current would be when I first throw the switch. Now, that current is going to be the same through the 1 ohm as it is through this R equivalent. Now I'll need to go back though a step, and this is where you want to do kind of the equivalent circuits. You want to go from here to here to here. So I'm going to work backwards, and I get this current. From this current across this this equivalent, I can get the voltage equivalent. Gotta look at my own work, and that's I get confused. So I get this current. That current is the same as, well, it's going to split here. So I need to get the voltage across these two so that I can determine these individual currents. I got to stop and think about what is it that I want. I want I2, this one. That would be the voltage across here, and just getting that voltage was what I was doing here. Getting that, and then I can get I3. So this is a classic case of just equivalent circuits. Yeah.
What do we count capacitor as a short circuit when we just flip the switch so there's no voltage in the capacitor?
Well, there's no voltage on the capacitor, so there's no voltage drop.
Right.
Also, the charge is really starting to pile on. Say, hey, we got a big bus here, and nobody's on, so you can go ahead and climb on.
Right.
So the idea that it just more or less does not obstruct the current flow at all.
Right.
The resistor, though, is probably going to control the fact that there's not a lot of current going to be just jumping on the bus ready. Okay. Let's go on and see if I have answered your question. Then the other key word, after a long time, the capacitor becomes fully charged. When it does that, it doesn't allow anymore. The bus is full, we can't get any more on here. So the idea is that there would be no current going into the capacitor. We say it acts like an open circuit. It's open here. The current through here was zero because the capacitor was full. Nothing else coming through. There's going to be, since there's no current here, there's no voltage drop. So it acts just, again, like an open circuit. Then once this is kind of out of the picture, it's fairly simple. You got 6 volts, 1 ohm, and 2 ohms. That's 3 ohms. You can come up with 2 amps are flowing here is going to be the current. Then we can look at that 2 amp current times 2 ohms. You get a 4 volt drop across V2. It's 4 volts across here. Now this is going to be key because when we flip the switch back on and this thing is going to start to discharge, we need to know how much voltage this thing was raised to. Now in the simple series case that we just dealt with, we just said, oh, the voltage of the capacitor when it's fully charged meets that of the battery. In this case, it's not quite true. There's going to be a voltage on the capacitor, but we're going to need to find it. That 2 amps that's flowing through here in this 2 ohm resistor, giving you 4 volts across this resistor, that has to be matched since these are really connected in parallel. That is, this branch is. There's no current here, there's no voltage drop, so I'm sure that the voltage here has to match the voltage across R2. So since that was 4 volts, I can conclude that this capacitor, it's fully charged, and it's fully charged with a voltage of 4 volts, and whatever the amount of charge would be from that. Okay, so the voltage of the capacitor, again, 4 volts. Okay, we need that to step to the next step, where all of a sudden now we're going to open the switch again. And when we, after the switch is opened, that's going to open up. It's really going to take out this whole part of the circuit. Even if this is still connected here, since I'm not going to get any current when I open this up here, no current coming in here, it's pretty much dead. And then I just simply have the idea of a charged capacitor, at least initially at 4 volts, is going to dump through these 2 resistors, R2 and R3, and these are in series, so I'll just replace it with an equivalent resistance. And now I have a simple discharging capacitor. And here's where I'd say, well, I know what the equation is now. I've already been through this a number of times, so I know that it's got to be the original charge, which is going to be 4 volts. Excuse me, the original current is going to be the effective this. Think of this like a battery. It's like a 4-volt battery for an instant going through 5 ohms, and that's going to be the current. And again, we can deal with the time constant if we want. But this is really an expression of the answer that he's looking for. He wants the current as a function of time after the switch is opened. And that would be really just this particular current. There would be, of course, no current in these other things. So both of these share the same current. So that would be answering the question, hopefully. Okay, does that make sense?
Good question.
Yeah.
The resistor 2 is keep on getting that current from a 6-volt supply, right?
This was, 6 volts.
Right. So that 6-volt supply will still push the current inside of a 2 ohm resistor, right? How can we calculate current in a loop with capacitor, including that 2 ohm resistor, when there's still going to be the same amount of current?
Now, let's see. I argued that this is after a long time, so I'm using the special case that the capacitor is full, and therefore no current's going to flow. And so now I just have a simple series circuit. So I'm not sure this is getting to your question.
How do we do part C, where there still be a current in a 2 ohm resistor, or we just take a top switch in part C and we just discharge capacitor? So my main question for part C is the switch open or closed?
Part C, the switch is open.
Okay.
Yeah, time t equal to 0, the switch is open. That just takes that out.
Yeah.
And then the picture looks like this.
Yeah.
Okay? And again, we want to warn you, it's not up to 6 volts, it's up to 4 volts is going to be the voltage on the capacitor.
Then my main question again would be, what is the initial current inside of that loop when we have 2 currents up there?
2 currents up? Oh, maybe my picture is maybe confusing. I'm just saying, okay, this is the picture of what we have.
Right.
And then I say, oh, these 2 are in series.
Right.
So I have an equivalent circuit. Just saying, okay, this is really 5 ohms, and that's what I'll use for my RC, 5 times the capacitance.
I'm probably overcomplicated it by saying that there is still a current from a left loop in the 2 ohm resistor.
Oh. I would say that once this switch is open, that kills this whole branch.
Right.
Nothing, and even if I have this connected here, there's nothing, this switch opens, there's nothing flowing out this way, there's going to be nothing flowing back in.
Right.
It's out of here.
That's why the current, there will be only the current between 2 resistors and capacitor.
That's right. It's shared just between them.
Yeah.
Okay, yeah, a lot of subtle reasoning on these, but this is a real typical exam kind of question. Again, watch the words when it's first closed or after a long time. That's what you want to deal with.
And the capacitance was given in the initial problem, right?
The what?
The capacitance?
Yeah, I see I've got it, I think I've got it written here, 100 microfarads. Yeah, I kind of jumped there. I should have written that down. But yeah, it's 100 microfarads. It was part of the problem. Okay, let's go on to magnetism. Okay, that was kind of real quick through circuits. A lot of people are in the circuits class, so this should be a piece of cake for you. if you're helping other people study and you're in circuits and you're trying to help them with their Kirchhoff's laws, do it according to the physics method, not what you learn in circuits. Don't do mesh analysis. That's really going to get them screwed up. So, help your friends. Don't.
Can we do a Norton?
Okay. Now, as far as you can. Now, you can do your circuits techniques. If you're on the problem, Dr. Young is fine with that. However, I'd say you better not make a mistake, because I don't think he's going to be as gentle on you as somebody that's just trying to do the physics method, where voltage drops are really voltage drops. They're not plus, Those are all sine games. It's all based on Kirchhoff's laws, but it's confusing enough without you adding to it. So, okay, magnetism. You played with refrigerator magnets. You know about attraction and repulsion. One word of caution: we've got this north and south. We've got this idea that opposite poles will attract, like poles repel. Very much like plus and minus charges that we dealt with here. And a lot of times you'll hear people say, they'll refer to north and south kind of interchangeably with plus and minus. And it's like, no. A magnetic field will not attract a charge like an electron or a proton unless they're moving. Then we get this strange effect, and it's like, let's see, how are we doing here on time? Quarter after, okay, actually, I think we're doing all right. Okay, the idea of, this is weird. I mean, you get a charge that's moving in one direction, you get a magnetic field in another direction, and you get a force in another direction. And like, who ordered this, It's weird. Now the cross product, I assume you've dealt with this before, like in a math class. QV cross B, so if I have B and V, B is going to be at right angles, the force is going to be at right angles to both of these. In fact, you want to start this first here. You want to get a clear sense of direction. What direction is V? Is it in the X direction, Y direction, Z direction? How about B? And then take those two and then decide that there's going to be a perpendicular. Your magnetic force is always perpendicular to both of them. Okay? Now, so consider that once you determine V and B and what plane it's sitting in, then you can determine what B is by, it could be either up there or it could be down. We'll use the right-hand rule to take V and cross it into B. So this is this kind of crazy rule that we take V and imagine your fingers pushing V in the direction of B, and then your thumb will come out in the magnetic direction of the magnetic field. But again, as far as sorting this stuff out, this is perpendicular to both of these, and that's fundamentally fundamentally where you want to start. Do you get the force in one direction for a positive charge? It's going to go off that way. If it's a negative charge, it's going to be the other direction. So you can use the right-hand rule for positive charges. Don't do like I did on an exam. I was writing away with my right hand and doing my signs with my left hand. I got -1, -1, -1. And you're going to probably look, I know you're not going to be looking at your neighbor, but you're going to be seeing people all over the room doing this kind of strange gyrations with their hands. So if you want to use the left hand for electrons, you can, but basically we'll be taking this form, and if the charge is a negative charge, that's just going to turn the force vector around the other direction. Okay? Yeah.
What did your knuckles indicate?
You're ready for a fight, I guess. I would do this a little more open-handedly. Yeah. The idea that you imagine putting the butt of your hand on the axis. So I know if I've got if I've got V and B, I say, okay, that's the plane of V and B. I know that the force has to be perpendicular. So it's either that way or that way. So all you need now is your right hand to sort out, is it that way or that way? You're going to take your fingers, imagine taking your fingers and pushing V into B. And then your thumb is going to say, oh, it's that way instead of the other way. Okay, takes some getting used to, and you can get in positions where it's kind of hard to visualize what's going on. Oh, quick thing, SI units for all of this is Tesla. There's other units like Gauss, but we're going to focus on just SI units. Oh, if you want, there's another left-hand rule that some people really like. That's where your fingers become like the magnetic field, and that your thumb is in the direction of the velocity, and then the force comes out of the palm of your hand. So it's a favorite among those with a persecution complex. They like that. Okay, so now one thing, magnetic field, and you're familiar with this kind of graphic convention. We draw dots if the B is coming out of the page, crosses if they're going into the page. Oh, yeah. So if we start with some charged particle in motion, and the magnetic field is going in, so I'd take my right hand and take that V and push it in because the magnetic field is going in, and the force is this direction. That's going to cause this thing to deflect. Now, one thing that's important that you realize is that the magnetic field, at least a static magnetic field, can't do any work. All it can do is deflect the charged particle. It's not going to do any work, so it's never going to change its speed. It's just will possibly change its direction, so its kinetic energy doesn't change. So the velocity is this way, but the force is that way. That's going to cause it to bend this way, and it's going to come around, still traveling the same velocity. The force will still end up having the same magnitude, and we can play this game along the entire path of this thing. And by symmetry, we can also argue that this is going to be a circular path that this is going to take. Again, the thing doesn't speed up or slow down. This is going to change in the next section, the first thing, when we say, well, what if the magnetic field is changing? Then it can create, do work on a moving charge. Anyway, more on that later. But for us right now, it doesn't do any work, just deflects.
Quick question.
Yeah.
I see that on the one that was emailed to us, there have been some changes.
Oh, yeah.
Will the new one be emailed?
I uploaded that. So if you downloaded the other one, just trash it. Hope you're not printing these things out. Go through reams of paper. So I did update that, and I added some more that we're going to be getting to, because I'm trying to, since you're not getting to Ampere's law, and there is typically where some real test questions are, he's got to give you something. So I'm going to try to help you strategize.
Where would this new one be? Is this on the...
Oh, it should be up on the same link.
Oh, it's on the same...
Yeah, so if you just click on it again, it should be updated. Yeah, so I kept the link the same. Yeah.
Was this magnetic force perpendicular to velocity?
Yeah. Yeah, the magnetic force is going to be perpendicular to both velocity and the magnetic field. That's the thing that... always, yeah. Yeah, the idea of V cross B, you want to consider that third vector, that force, is got to be perpendicular to both of these. And so that the magnetic field's in, the velocity is here, so that if you have to play with it a little bit, V crossed into, V... right hand, right? V crossed into B is a force in that direction. Also, for us around here, these have 90 degrees between them, so we can get by with the magnetic force is just QVB. That. And then, since this thing is going to be traveling in a circle, F equals ma. This is the force is equal to the mass, and for a circle, it has to be V squared over R. So we can solve for, let's say, maybe solve for the radius of this if I know all this other stuff. And this is what we're going to be playing with. Well, let me get to some examples. How about the good old mass spectrometer, which is something close to what we did in the lab this last week, only we had electrons. It kind of comes in two parts. I need to know the speed of something, so typically we'll get some charged particle. Usually it's some maybe atomic nucleus or something, and we give it a single ionization or double ionization, and then maybe put it in an oven, and all of this is evacuated, and we heat it up, and then we open it up and let charged particles come through. And they're going to be shooting through at different speeds, and so we want to pick out a particular speed. So we can do that with this idea of the velocity selector. The idea is we're going to have a magnetic field along with an electric field this way, right angles to one another, and we're going to bring in a charged particle traveling with some speed v. Now the electric field is going to try to bend it this way. So if we had the magnetic field shut off, it would come over this way, like a projectile. Then we also have, with the magnetic field, V crossed into B should be a force back in the other direction. So if we had a magnetic field without the electric field, it would bend off this way. So we can balance those two. For the velocity selector, we've got the magnetic force. Since they're at right angles, it's just QV times V. We don't need to go cross product. It's QVB sine of 90 degrees. That's going to be the magnitude of that force vector. Q times E would be the force on that charge from the electric field. Turns out it doesn't matter what Q is. That's going to cancel, and we get the velocity is going to be equal to E over B. So depending what velocity I want to tune this thing for, I can tune my electric field and my magnetic field such that will pick out the velocity. Again, if it's traveling too slow, it goes this way. The electric field wins out. If it's traveling fast, the magnetic field increases its force with speed. So the faster it's going to go this way. So the fast ones go this way, the slow ones go that way. The ones that are just right go through the little window. Then they can enter this magnetic field, and they would go in a circular path. They typically don't go in a full circle. They come over and smack into a detector over here. And then we can measure the radius of that and determine the... I think I did this a little... well, this would be the radius of that. I think I just borrowed that from the previous slide here. Yeah, the radius is this. You can follow the reasoning here, and we just make use of that here. So it's kind of the same thing. It's just going to be on a circular path. Typically what they'll do is want to solve for the mass of this thing, get the mass of this particle, and we can get that from these parameters here. Okay. Now, we also can have a magnetic force on a current carrying wire. And the idea that we get some, let's say, section of wire. I've got one charge that's in motion. On average, they'd be going with the drift velocity. But we could have a whole bunch of these, and there'd be this magnetic force on all of them. And that would contribute to the overall force on the wire. So we can say, okay, that magnetic force is equal to N. I've got big N represents the total number of charges that are in motion here, times the force on an individual charge. Now we can get the number that are in this section of wire. That would be the number density times the volume of the wire. The length of the wire times the cross-sectional area would be the total number. And then also if we bring in Q, we get this little combination here, Q and VD, NQ VD times the area. Now you might remember this or hopefully you remember, was the current density in the wire times the cross-sectional area would be the current in the wire. So this is kind of a little corollary to the magnetic force for a single particle. This is going to be the magnetic force for a wire. Now, the V should be in the direction of the motion. We're assuming these charges are moving along the length of this thing, so we usually write as far as the cross product. Rather than the velocity, we write it in terms of the vector L along the length of the wire. But this would be the force, magnetic force on a wire carrying a current I of some length crossed with whatever the B field is. And so, again, that force is going to be perpendicular to both the length of the wire as well as the magnetic field. Okay, how are you doing? Are you... Okay, let's go a little more and then we'll take a break.
Could you go back on the Wi-Fi? Yeah.
Oh, wait, wrong way.
Yeah.
Oh, what I was saying?
Yeah.
Okay, the idea of, we know that for a magnetic force on a given charge that's moving inside the wire would be its charge times the speed it's moving, the drift velocity, cross B. This would be the force on one of them. We're going to have a whole bunch of them. So if I have N in there, we're going to follow that. Now, maybe I'm getting confused in all the symbols that are flying around here. I get the total number that are in there by the number density that's coming back again. That first showed up when we first started talking about current and current density. Times the volume of that wire. Its length times its cross-sectional area would be its volume. Times the number density should give us big N, the actual number of charges that we have moving. They're each moving with, on average, the drift velocity. We can combine these terms together, bringing the L out and making it in the same direction as the velocity vector. And grouping these terms together, this is maybe not obvious. This was back on like the second slide, first slide actually. This would represent the current that's in the wire. The number density times the charge times the drift velocity, that's the current density, times that area will be the current. Now, if that's confusing, I mean, I'm throwing a lot at you here, go back to that very first slide to sort this out.
Is the speed of the current?
The drift velocity is the average speed of the current. Yeah, and that's where we're coming with the drift velocity. Now, if you followed that, that's fine. Hopefully, at least you conceptually get the idea and realize that this is just a corollary to QV cross B for a wire. Okay, and we'll use that now with forces on wires. We're going to do the torque on a current loop. And these are things that I'm thinking that if he's looking for something to hit on an exam, he doesn't leave himself too much more room. So I think we want to look at this. The idea of this is going to be a simple rectangular current loop where current might come in here, go around the thing, and come back out. So we'd be looking something like that. And we're going to take a couple of different points of view. A lot of this with this cross product, and you're dealing with all three dimensions, it can be very, very confusing. And you'll see a lot of diagrams, they get nice drawn three-dimensionally, and you'll start playing with them and you realize this is confusing. They're ambiguous. They're on a flat piece of paper. But the best thing to do is to start to take different points of view. So if we start with just a current loop here, and here we're starting with the magnetic field in the plane of the board here, and this is also in the plane of the board. And then we look at it from the point of view of the side. We're doing this way, so the magnetic field is this way in the same plane as the loop. The loop is like this. Then we can start to look at things. The current that's going in here, the current going this way here is going to go back here, is going to go into the board here, and is going to go back in space. It's going to end up coming around back this way. On this side, it's going to be coming out towards you, and we have that coming out there indicated by a dot. So this kind of purple here, the current's going in, up the back side, out here, and then the front side, it's coming back again. So you want to kind of convince yourself of that. The dimensions of this loop are A and B. This is going to be B across here from this point of view. So you want to be able to kind of do this in your head on a piece of paper. You should be able to draw this stuff out. I'll show other examples where it really helps to take this kind of a point of view. So this first one is relatively simple. We've got the magnetic field coming in. We've got this wire coming out, so that's V crossed into B is a force that's up. So that's on this wire is an upward force. Then we come around to, there was the current coming out. Now the current is, well, okay, the current coming along this way and the magnetic field, they're in the same direction. So what about the cross product of these? Zero. Yeah, what is the angle between them is 0. So the sine of 0 is 0. There is no force on this wire. And also on the back side where it's going back the other direction, there'd be no force on that. This one has the current going into the board. That current with the magnetic field, let's say, into the board, I need to take that current and curl it into B. So I'm going to go in, B is this way, and curl it this way so that I get a force in that direction. So hopefully you can kind of do this stuff in your head. It definitely gets some getting used to. Now this is going to give us really a torque on this thing. Notice the net force is 0. So this loop isn't going to start to just, start to move around or translate, but it is going to start to rotate. And as it rotates, it's going to come up to something more like this. This is a little more of something in between. Where the thing comes up like this. We've got, again, the current is coming out at us. In this case, it's kind of the same sideways point of view. B is coming this way. We can go, the current crossed into B is an upward force. Coming down this front side, there actually is a little force on this thing, or in that the current is coming this way, the magnetic field's this way. V crossed into B is going to be is going to be a force that's directed inward. If you play the same game on the wire that's on the far side, it's going to be in the opposite direction. So those two forces, they don't lead to any kind of torque. They will just kind of push into one another, and they will not give us a net force. They more or less just cancel. The forces that we're going to be interested in are these two forces. Well, I just did the wire coming out at you. If we have another wire going in, V crossed into B. V is that way. I need to cross it into B. Got this wrong. V crossed into B. This is where you got to kind of get like this. This is where it gets to be difficult. V crossed into B is a force down. Okay. Okay. So let's look at what the how the math works out here. Remind you of what torque is. R cross F. So we've got these two forces. The R cross F, the R would be the radius out to this point. It's going to rotate around this point. So R would go out that way. F would go around. That too is a cross product. So we got all these cross products going on. This is helpful. And just for one of these, let's say this wire, the R is going to be B over 2. So this whole side was B, so this is B over 2 times the magnetic force times the sine of the angle between them. That's going to be this theta. Yeah, sine of theta. B over 2 times the sine of theta is, and then, okay, and then the magnetic force is going to be ILB. The sign between the current and the magnetic field is 90 degrees. Current is going in here. It's 90 degrees to the magnetic field that's happening there. Whew. Okay. Confusion, okay? Now, we have the torque due to this one. We also have the torque due to this one. So that's where this factor of 2 comes in. I've got 2 of these, both contributing to a torque that wants to twist this thing like that. The net torque on this thing is going to be, when we come in here, we're going to have an A times B. A times B is going to be the area of that loop. So we can write this as the torque is going to be IA times the magnetic field, A being the area of the loop, B the magnetic field, times the sine of the angle between them. And we can formalize this even more with making yet another cross product here. That we can say that the A, the area, and make it an area vector. This is something we're going to use in the future a great deal. This area vector is pointing at right angles to that loop. So if we have that loop, the area vector pointing out would do this kind of thing, going in that direction. And the torque actually wants to get this thing to twist and turn and face the magnetic field and go along with it. So it kind of torques around a bit like a compass needle, where it's going to want to line up with the field, and that would be the direction of the torque. Yeah?
Is there any force caused by the 2 wires or sections of the square?
The front and the back side?
Yeah, but the current's moving like that.
Yeah.
So there's
there is a force. Consider that, okay, the current is coming this way on the front side. V crossed into B is a force that's out of the board. I think I had that wrong. I stated that wrong earlier. Yeah, V or the current crossed into B is out this way. So there is a force. It is this way, and it's not leading to any torque. On the far side, since the current's going the other direction, there's going to be a force in the opposite direction that would be equal. So between the front side and the back side, they're going to cancel.
Wouldn't that want to make like the entire thing kind of scrunch in?
Okay, yeah, would be a tendency it would want to cause it to collapse. Or wait a second, no, excuse me, expand. It wants to blow it apart. And that is true. There is a pressure, if we like to make a solenoid, there is a magnetic pressure that's very difficult to contain this. And NMRs are notorious that they have to hold this thing together because these things want to blow it apart.
So we just ignore those?
Yeah, as far as the torque, they can be ignored. The net force on the whole thing, these 2 forces cancel too. But they do give a torque. But consider that on a loop, if I apply a force on one of the sides, it can do that. But if I'm applying a force out this way, that's not going to lead to any kind of torque. And that's the problem with the front and the back sides of that.
That's the reason why they have alternating currents, things like this. Because once it would reach the maximum of when theta is equal to 0, here's the diagram, force would be putting straight down.
Yeah.
But once they get just a little bit further, if you switch the direction of the current, then it...
Oh, okay, yeah. As far as being able to turn this thing into like a motor, that's where, yeah, you would be changing your magnetic field. You have that. Anyway, Dr. Young, he probably did motors for you, didn't he?
Maybe 120, physics 121 question, what is the location of the changes?
What?
We changed this location of the hinge.
Oh,
Yeah.
okay. This thing is just kind of sitting out here. Now, if you hinge it somehow, we can show that it still has the same torque. It can rotate about a different axis. This would still be valid. Yeah. So if you're mechanically restricting its motion, you could get it to do this kind of thing. Okay. But let's see. Right now, I don't want to get too much more into that. It's true about torque in general. We could do that like as. Oh yeah, you have got one here. Okay, it is hinged around the one. You could try this either way. You do this, or you just say, hey, forget this one. Just deal with the force on the one side. You end up with just one force, but you have two B's, and so you double your moment arm. So it comes out the same. So trust that. Okay, let's see. Yeah.
How do you determine the direction of the area vector?
Oh, okay, good question. Yeah. Okay, hold on just a second, then we will take a break. But there's one little addition to this. Is this idea of the area vector. Also, let's say, back here a second. Okay, we've got this. I drew the area vector this way. The fundamental of this is that the current going in here, if we're going around a loop, is going to go in such a way, using again another right-hand rule, that the area vector is going to point this way. Now, this thing about the loop, the loop doesn't have to be a rectangular loop. We had this and all the problems associated with it. It turns out that you can make any shape loop and really base it on a bunch of rectangular elements that just get stacked together. But the idea, it can be any shape at all. And so the idea of the torque on a current loop would be mu naught A, where A is the vector. And again, this can be any area. The loop can be of any shape, like a circular shape, like this. And as far as the direction of the area vector, this is probably easiest to see on this kind of a loop. You'd take a loop like this. If the current is going this way, with your right hand, it's going to point, and this is going to be the sign convention for the area vector, rather than the other direction. So we'll use this definitely in the next section. Yeah.
On a test, would he be asking for like max torque or something like that, or?
He could, sure. You would kind of play with in your mind what kinds of games you're going to have, or he might play. There is going to be a torque that is going to be coming around. The maximum torque, I think you'll see, is actually back here. Yeah. And it's going to start to torque around. It wants to line up with the field, so I guess maximum torque would be back here. And maybe...
But I mean, because there's not a whole lot of like practical stuff that you can do.
Yeah, so that's where your creativity, as far as, what could he ask? And I'm going to have some thoughts on that also, as far as what he might do to try to counter that you don't have Ampere's law to play. He doesn't have Ampere's law to torture you with. So, again, this idea, this gets used a lot. The current times that area, we can make a vector, mu. Actually, this should be a mu sub b. Usually there's a little subscript there. This is called the magnetic moment. I don't have that up there either. So very often it's done this way, where you just take this as this, and then we take the cross product between mu and b. And this would be a handy one. If this is mu, the current's doing this. And if the magnetic field is, let's say, back this way, it wants to torque around and line up with the field. Okay, I think this is kind of more of the same. Okay, let's see, with the Hall effect. Do you want to take a little break now? Yeah, let's do that. And then we'll come back to the Hall effect. Just a second, I want to shut off this camera.